There is a hidden heartbeat to our entire world, a constant, invisible pulse that keeps everything running. But what happens when that pulse starts to fail? Today, we're talking about a very specific number, a tipping point that separates a perfectly normal day from a potential nationwide blackout.
You know, you could be sitting in your house right now, the lights are on, your Wi-Fi is working, everything feels perfectly fine. But deep inside the electrical grid, a massive, invisible balancing act is happening every single second. And sometimes, that balance can start to tip.
So, to really get what's going on, we first need to listen in on that hidden rhythm. It's the absolute foundation of our power grid. And once you understand it, everything else just clicks into place.
Okay, so you hear this term all the time, grid frequency. But what does it actually mean? What is it we're measuring? Honestly, the best way to picture it is to imagine the entire power grid as a giant continent-sized orchestra. Every single power plant, whether it's nuclear, solar, or wind, is a musician. And grid frequency is the tempo. It's the one perfectly synchronized beat that every single musician has to follow. In many parts of the world, that beat is exactly 50 times per second, 50 hertz.
And here's the key. That tempo isn't random. It's a direct result of a perfect balance. The music is our demand. It's us, turning on lights, charging cars, running factories. The musicians are the power plants generating that electricity. When the power being made perfectly matches the power being used, the tempo is a rock-solid 50 hertz. But if demand suddenly jumps up, like on a hot day when millions of AC units kick on, the musicians can't keep up, and the tempo of the entire grid starts to slow down.
And that slowing tempo brings us right to the edge, to that critical tipping point. The system is built for a perfect rhythm, but what happens when that rhythm starts to break down?
Now, don't get me wrong, the grid is incredibly resilient. It can handle little wobbles. The frequency can dip to, say, 49.9 hertz or go up to 50.1, and that's totally fine. It happens all the time. But there are hard limits. There are lines in the sand that are not meant to be crossed.
And here it is, 49 hertz. When the grid's tempo drops to this level, it's not a wobble anymore, it's a 5-alarm fire. It is the system screaming at the top of its lungs that it's about to be overwhelmed. It means the demand for power is dangerously outstripping the supply, and a collapse could be just moments away unless something is done about it, fast.
But when that alarm goes off, the grid doesn't just panic and fall apart. No, it's smarter than that. It has an automated, pre-planned emergency protocol. It's designed to try and save itself.
It's a process called under-frequency load shedding. Sounds technical, but the idea is simple. First, sensors all over the grid detect the dangerous drop in tempo. The system knows, instantly, that there's way too much demand for the number of generators online. So to save the entire orchestra, it has to make a calculated sacrifice. It intentionally and automatically starts cutting power to certain areas. That's load shedding. The goal is to instantly reduce the amount of music being demanded so the musicians who are left can catch their breath and get the tempo back up to a safe level.
It sounds harsh, right? Cutting people's power on purpose? But it's a brutal but necessary choice. The system has to hurt a few to avoid a catastrophic, uncontrolled failure that could knock out power for everyone for days or even weeks.
But what happens if that first sacrifice isn't enough? What if cutting power to a few neighborhoods doesn't stop the tempo from dropping? Well, this is where you get into a truly terrifying scenario, the domino effect.
So remember our perfectly balanced grid. On a normal day, this is what it looks like. Supply and demand, our musicians and our music are in perfect sync.
And then, bam, something goes wrong. A major power plant, a huge section of our orchestra, trips and goes offline without any warning. It just disappears.
The result is immediate. The demand for power is still at 100%, but our ability to generate it just took a massive hit. That huge gap between supply and demand is what causes the frequency to go into an absolute free fall, way past that 49 hertz warning sign.
Now, think about the power plants that are still running. They're being strained like never before, trying to make up for the one that was lost. This puts enormous physical stress on their machinery, their turbines. So to prevent themselves from literally tearing apart, their own safety systems kick in and they shut down too. And that is the domino effect. One generator goes down, which overloads the next one, which makes it shut down, and on and on. That's how a small problem can cascade into a massive regional blackout.
So let's say the worst happens and the whole grid goes down.
Why does it take so darn long to get the power back on? I mean, can't they just flip a big switch somewhere?
Well, no. It's a procedure called a black start, and it's one of the most delicate and complex operations imaginable. Think about it. Our orchestra is totally silent. There's no tempo to follow. You have to wake up just one musician, get them to start a steady beat, and then very carefully bring in the next musician, making sure they are perfectly in sync. Then the next, and the next. You have to bring every power plant back online one by one, and then add the cities and towns back just as slowly. If you do it too fast, you'll just create another imbalance and the whole thing will collapse all over again.
Now, there's a reason we're talking about all of this today. It's because this entire balancing act, this job of keeping the orchestra in time, is getting much, much harder than it used to be.
Our energy orchestra is fundamentally changing. We're adding all these new, sometimes unpredictable musicians. Renewables like wind and solar are amazing, but they only play when the wind is blowing or the sun is shining. At the same time, we're asking the orchestra to play much more demanding music, like millions of electric cars all plugging in at the same time. Trying to keep this new, more complex orchestra perfectly in sync is one of the biggest engineering challenges of our time.
So if you only remember one thing from this whole explainer, please let it be this.
A huge power outage almost never happens like flipping a switch. It's not a single sudden event. It's a process. It's a system unraveling, piece by piece. It starts with a small imbalance, a drop in frequency, a missed safety check, and then the dominoes start to fall.
And that's exactly why understanding this hidden rhythm is so crucial. Because once we understand how the system can fail, we can start to build a smarter, stronger, and more resilient grid that's ready for whatever the future throws at it.
So, that's the hidden story of what happens when the grid's heartbeat falters. If this finally made the whole thing click for you, you'll probably really enjoy the other explainers we have on this channel. Thanks so much for watching.